Patil, and today here I am going to explain variational method, which is from quantum mechanics. So today let we start this variational method from its basic principle. Now, in other approximation method, we can solve the problem, or we can find the energy eigenvalues by considering the first step as h is equal to h0 plus h0. Okay, so here h is the Hamiltonian of the given problem, and h0 is the unperturbed Hamiltonian, where h dash represents the perturbation into that system. But in case of a variational method, we need not to have this splitting of Hamiltonian, or we can say when we don't know the components of h in terms of h0 and h dash, then also we can solve the problem, or we can find the energy of the system. But here another thing that is useful by this variational method is that to solve the problem we need not to solve Schrodinger wave equation here. To solve the problem by variational method, we need not to solve Schrodinger wave equation. Hence, this is quite interesting method to solve the approximation problems in quantum mechanics. So let we start this variational method. In this variational method, first we have to guess a wave function by depending on the physical conditions. First we have to guess a wave function, and that wave function, if I consider a psi, this wave function is used as a trial wave function, and by using this trial wave function we have to construct the expectation value of the Hamiltonian. Directly we have to construct the expectation value of Hamiltonian with respect to the trial wave function, and then this expectation value with respect to trial wave function is greater than true eigenvalue of the state. This is the basic principle of variational method. So again I will repeat, the expectation value of Hamiltonian with respect to trial wave function is equal to or greater than the ground state energy of the true gate. Okay, this is the principle of the variational method. So this expectation of h can be written as expectation of psi naught h psi divided by psi naught. Okay, so this is greater than or equal to the ground state energy. This is the basic principle of this variational method. Now let we understood the proof of this principle of variational method. Okay, let we start it's a proof of the variational principle. Okay, now we can understand this. First thing is that we have to guess a trial wave function. So if I consider size 0, get size 0 is the trial wave function. Now to guess this trial wave function, we have to consider its conditions, that this trial wave function should be vanish at infinity, or this trial wave function can be written in the form of linear combination of eigenkets of Hamiltonian. If we say H is the one Hamiltonian and ket phi n are the eigenkets of this H, then our trial wave function can be written in the form of linear combination of the eigenkets of the Hamiltonian. So this is equal to the sum of the something constant. If I say it is an and ket n, so this is the our trial wave function. Then we have to take its conjugate, that is bra size 0, which is the complement of this size 0. Okay, and that should be written as summation of m, like am star, and here there is bra phi m. So these are the our trial wave function. Now what is this? This is expectation of H. Now expectation of H is can be written as, this is summation over n, summation over m, am star, and here there is bra m h ket n. Now this gives us the expectation value of H. So we can solve this as like this. So again we can write expectation of H, expectation of summation of m, summation of n, am star, and here one thing is known, that H phi. So as this phi is the eigenket of H, then it gives us E phi. We already know that H phi n is equal to En phi n. This is the condition when this phi is the eigenket of H. By using this, we can write En phi m phi n. Okay, this is the expectation. Now if we go in the next step, here we can see this is the Chronicles delta. Chronicles delta, where we know that this is we can say it is the inner product, and this m is equal to n, then the inner product will becomes 1, and when m is not equal to n, then inner product becomes 0. So this term will vanish when m is not equal to n. So we have to take only those values for which m is equal to n, because all the terms where m is not equal to m will vanish. So we can write this as summation over n. If m is equal to n, then we can write this as mod an square. This is an, and this is star, so we have to take modulus of this an square into this en, and when m is equal to n, this term or this inner product will be 1. This is 1, or we can cancel it. So finally we have got this expectation value of h is equal to summation over n mod an square into this en, where en is the energy eigenvalue. Okay, this is the expectation value of h. So that we understood the next procedure. Here we got expectation of h is equal to summation over n mod an square into this en. Now what is this an? N will be 1, 2, 3 and so on. So we can split it as a1 square e1 plus a2 square e2 plus so on up to n. Now another thing, we know that what is e1? e1 equal to e1. Simply E1 is the ground state energy or the energy of the first state. Now what is E2? E2 is the first excited state or the second state energy. Then we know that E2 is equal to the E1 plus something additional term, that is we can say delta E2. That is the difference between E1 and E2 energy. This way we can write E2 is equal to E1 plus something delta E2. And if we substitute these values here, then it becomes A1 square E1 plus A2 square into E1 plus delta E2 plus A3 square into E1 plus delta E3 plus so on. In this way we can split these terms, and again we can rearrange the terms as right here. We can rearrange the terms as A1 square E1 plus A2 square, here A2 square into E1 plus A2 square into delta E2 plus A2 square delta delta E2. Then A3 square E1 plus A3 square delta E3. In this way we can write. Now if we collect the terms A1 square E1, A2 square E1, A3 square E1, these terms, then we can take E1 common from this A1, A2, A3, and other terms, those are A2 square delta E2, A3 square delta E3, we can write in the separate fashion, and then we can get as like this: summation over n mod a n square E1, because here A1 square E1, A2 square E1, A3 square E1, and all the terms we can collect here. Then we can write summation over n an square E1, and the remaining terms can be written as summation over n starts from 2, then summation over n equal to 2 mod an square, and here there is delta En. In this way we can write. Now another thing, we know that what is an square or a1 square. A1 square gives us the probability of finding the system in the state 1, that is the eigenstate E1 or first eigenstate. So if we add all the probabilities of the system finding in each eigenstate, then it becomes the total probability of the system, and we know that the total probability of the system is 1. So this summation of an square will become 1 because it gives us the total probability of the system. Then we can write this is equal to 1 into this E1 plus this summation over n equal to 2 to infinity, or the terms mod an square delta En. Okay, now again if we write clearly here as expectation of H is equal to, that is E1 plus something extra terms, we can write extra terms. Then automatically we can write it as expectation of H is equal to or greater than E1. If extra terms are 0, then it will be equal to E1, and this term is non-zero, then condition will also satisfy that expectation value of Hamiltonian for the that trial gate is equal to or greater than E1. That E1 is our ground state energy or first state energy here. So this is the principle of the variational method, and here this is the expectation value of the Hamiltonian with respect to the trial wave function. This gives us the energy eigenvalue for ground, and this method mostly used to find the ground state energy. In few cases we can use this method to solve the first excited and the second excited state also. So basically this is the principle of variational method, and we will use this for the solving the perturbation problems in quantum mechanics. Thank you. I hope you understand this concept, and in the next lecture I will explain how to apply this method to the various problems.